Hello, everyone. Thanks for joining us. We have a great crowd today. Welcome to the C2 Smart webinar series. My name is John Patinos. I'm a project manager at C2 Smart. The webinar series will be recorded to the C2 Smart YouTube channel, so you're welcome to check it out afterwards there. Today, we're going to be with Dr. Joseph Chow, Deputy Director of C2 Smart, and doctoral candidate Yueshuai Brian Hu. They'll be presenting their work on open source multi-agent virtual simulation testbed and applications for congestion pricing and COVID-19 pandemic recovery. If you have any questions for our presenter, please feel free to type them into the chat box at any time at the bottom of the screen, and I'll be reading the questions out loud to the hosts at the end of the presentation. Dr. Chow, please take it away.
Thanks, John. Welcome everyone. Good afternoon. Thanks for attending this webinar. So this webinar is intended to give an overview of the work that we've been doing with this virtual testbed that we've developed in the last 2 years to address some of the issues with evaluating new transportation technologies and policies emerging from various cities, using New York City as a first case study for this. Given the timeliness of the situation we're in with the COVID-19 pandemic, we also spent a few weeks looking into using this simulation testbed to evaluate the impact of COVID on the community in New York City, and also to show how we can potentially use this as a solution to help policymakers plan for reopening strategies with the transit operations later on. So primarily the presentation will be given by Brian. He's a fourth-year PhD student. He's looking to defend his dissertation later this summer, and part of his dissertation involves the development of this testbed. So I will let him take it away, and I'll be around to help answer some of the questions towards the end. Okay, so Brian, please go ahead.
Okay, thanks. Hi everyone, good afternoon. Thanks for attending our C2 Smart seminar. I'm Yueshuai Brian Hu, a PhD student of Professor Chow. So today, the topic of my presentation is open source multi-agent virtual simulation testbed applications for congestion pricing and COVID-19 pandemic recovery. First, I will talk about the research background of our work. It is a combination of 2-year project, the C2 Smart Year 2 project focusing on the development of the virtual testbed. And the C2 Smart Year 3 projects, we concentrated on like tech transfer from the virtual testbed. We have 2 collaborators. First, the NYC DOT, June Park, shared data with us. And the second collaborator is ETH Zurich, Milos Balak. He supports our development work. And we have a large team, consists of 10 students, PhD, master, and also undergrad students. The research objective is to build a virtual testbed ecosystem. There are 3 participants: C2 Smart Center, public agencies, and the technology providers. So our C2 Smart Center, we will build the base model of the simulation testbed, and we can help the public agencies to like evaluate their field pilots and also city deployment and give them feedback. And on the other side, we can help the technology providers to evaluate their live prototyping and also new technologies. And also like in the future, now we use the New York City as the first example, and then in the future, we can help other like C2 Smart collaborators to build their own simulation testbed. So let's talk about New York City first. What are the impacts of these scenarios? First is the BQX, Brooklyn Queens connector. It's a new streetcar services connect Astoria in Queens and the Red Hook in Brooklyn. The second one is the Citi Bike Expansion plan. The operator has a plan to like double their service area in the next 5 years. What's the impact of this? And the third is the test of autonomous vehicle in the city. Another hot topic is congestion pricing. Should we charge congestion pricing in Manhattan, or how many we should charge for it? And the most important currently, what about the COVID-19? What impact of this pandemic on the transportation system of the city? There are some existing tools can help us answer these questions, NYBPM, New York Best Practice Model, BTA, the Balanced Transportation Analyzer. These are two existing models, and also other simulation tools like MSUM, VSUM. But these existing tools have some limitations. They don't have incorporate the emerging modes like Citi Bike and autonomous vehicles. And our solution is a MATSim, multi-agent transport simulation. As the name indicated, it's an agent-based simulation. So during the simulation, we will simulate the travel behavior of every agent. There's two figures in this page showing what MATSim can do. The first is the activity simulation. So different color means different activities of agent. Like with time goes by, different activities appears and disappear. And the right side is a public transit simulation. In our simulation, we can simulate the complex transit system in MATSim. And also for MATSim, it adopted the co-evolutionary algorithm to find the equilibrium of the transit system. Actually, it's adopted day-to-day adjustment. Each iteration of MATSim represents for one day, and agents can learn some experience from their previous day, and they will adjust in the current day, day by day. After enough iteration, MATSim can get the equilibrium state. So there are lots of features of MATSim. First is open source, it's free for everyone, and you can support large scenarios. It is really important for New York City because we have 8 million population and a really complex road network and the transit network. The third one is MATSim. It has external module approach, which means it is feasible for anyone to develop their own module to focus on different topics like car sharing, bike sharing, etc. And also, since MATSim is an agent-based simulation, it has versatile analysis and simulation output. So the MATSim output will include all the details of the travel plan of everyone. So a lot of information can be extracted from the output. The figures on the bottom shows the famous MATSim loop, how they use the co-evolutionary algorithm to reach the equilibrium state. There are 4 components of our virtual testbed based on MATSim. The first is synthetic population. We developed 8.24 million population in 2016, include people's personal attributes, household attributes, etc. This is a demand side. And the second component, we have the modal networks. We have road networks from OpenStreetMap and transit network from GTFS. This can act as the supply side. We put both the demand side and the supply side into MATSim. You need to calibrate the road network. So for the road network calibration, we used ERIC speed data, NYC AADT data, and also a bridge tunnel volumes data in 2016 to calibrate our road network. The last one is a scenario analysis. Based on our synthetic population and MATSim simulation, a lot of scenarios can be analyzed. Here are some examples like Citi Bike Expansion, Amazon's new headquarters, congestion pricing, COVID impacts, etc. The first 3 components we categorize it as a mode preparation, and the last one is a scenario analysis. So in the rest of this presentation, I will introduce for each part. First, let's talk about the model preparation. The synthetic population, the first component. There are 3 steps to generate a synthetic population for New York City. The first step, population synthesis. That means you need to create 8.24 million people and with their personal attribute or household attributes. The second step, agenda assignment. That means you need to assign a travel agenda to everyone in the last step. And the third step, model estimation and model simulation. Due to the limitation of data, we only estimate a mode choice model and resimulate the mode choice for the 2016 synthetic population. The population synthesis, we adopt the population synthesizer PopGen is available by the link. So anyone can go through the papers and how to use that tool. For this project, all the attributes are aggregated to the TAZ level, the figure on the right side showing the TAZ system we used for New York City. Here are the list of attributes we incorporated in our synthetic population. We have person age, school enrollment, household size, and also industry, employment, lots of informations. And the data source we used list in the bottom. Here are some spatial distribution of attributes we have. This one is about the population density. This one is about average household income. And this one is about number of employment per TAZ.
Let me just chime in here really quickly. The LEHD, the industry for employment, that will come into play, especially later on when we show the COVID analysis to show who's working from home and who's essentially employed. Okay. Yeah, go on.
Okay. When we finish the population synthesis, we do a validation to validate the accuracy of our synthetic population. So we aggregate the attributes in the city level and compare to the existing observed data sites. We can see in terms of all the attributes here, the maximum difference are all less than like 10%. And on average, all the attributes have an error less than 5%. The second step, agenda assignment. Like when you're talking about an agenda, that means it has like a multi-dimensional choice, like activity purpose, destination, departure time, the duration, mode, etc. So as I talked before, we only do for mode choice due to data limitation. The data source we use for agenda and also the mode choice model, at least on the right side. And the mode choice model, we proposed a nested longitudinal-based model to estimate the people's mode choice. We have two levels. First level, you decided driving or not for the whole tour. If you decide not driving, you can like select all the alternatives in the second level for each trip in that tour. For each mode, travel cost and in-vehicle travel time were considered, and the availability of public transit and Citi Bike were also incorporated. For the model, we have two segments, Manhattan versus non-Manhattan. And we also incorporate emerging mobilities, like for hire vehicle and Citi Bike. The modes in the bike box are estimated from the 2010-2011 regional household travel survey. At that time, there's no Citi Bike and for hire vehicle. And so we want to actually, our model is based on 2016, and Citi Bike and for hire vehicle is really important. So we incorporate these two new modes by using new data source, 2016 Citi Bike and for hire vehicle trip data to incorporate this new, these two new emerging modes into our model. And last, we have a smartphone ownership data, smartphone ownership model into our model to improve the performance. Here's the results of the estimation results of Manhattan segment for the 2010-2011. The value of time we estimated is about like $29 per hour. Here is the results of the smartphone ownership model. As we can see, for the age group and income group, we treat it as a categorical data, the category list on the bottom. And if we look at the age group, they have negative coefficients. This means like elderly people are less likely to have a smartphone. And if we look at the income group, as income increase, the coefficients increase from negative to positive, which means like higher income people are more likely to have a smartphone. To incorporate the for hire vehicle and Citi Bike, we use the least squares estimation to estimate the parameters for Citi Bike and for hire vehicle for both segments. And we also conducted a bootstrap sampling to like validate the significance of the variables. Here we can see all the variables are statistically significant.
Note that this is in addition to other attributes that are assumed to be the same to either bike or to taxi. So it's in addition to those parameters.
Yeah. When we finish our mode choice resimulation for the whole synthetic population, we do another validation against the 2017 Citywide mobility survey. So we can see in the figure, the prediction of the 2016 population is much closer than is much closer to the Citywide mobility survey, comparing to the other two, like 2011 household travel survey and 2016 trip-based model, which means like the tour model structure is more accurate than the trip-based model, and the aggregate level mode share is pretty close. The second component, modal networks. Our road network transferred from the OpenStreetMap. You can download the New York City, the OpenStreetMap data of New York City on their website. You can also download your own custom areas through their API. The transit network and schedules comes from GTFS data in September 2016. All the vehicle capacity is calibrated. The third component, road network calibration, we do in two sides. First is the speed calibration. For the links, we first classify all the links into expressway and arterial, and apply the average in-rig speed into the closest link in MATSim network with the in-rig's average speed showing in the table. And for the link capacity calibration, we use SPSA, simultaneous perturbation stochastic approximation method to help us estimate the link capacitor factors applied to the MATSim network. After 5 iterations, we get the acceptable results. We conducted a validation of the simulated volume to the real traffic count. 2 screen lines are selected. First is Hudson River screen line, includes George Washington Bridge, Lincoln Tunnel, and Holland Tunnel. Another one is East River screen line, including the Queensboro Bridge, Midtown Tunnel, Williamsburg Bridge, Manhattan Bridge, and Brooklyn Bridge. The validation results are shown here. We compare the 2 screen lines in each time period. The simulated volumes are close to the real traffic count. And we also compare our estimation difference with the NYBPI model. On average, NYBPI model has a volume error in 40%, and our MATSim model has only 14%. And if we look at the max difference, NYBPM is about 57%, and MATSim model is about 42%. So now we finished the model preparation. Let's go to the scenario analysis. The first scenario is the Amazon headquarters. This one is based on the synthetic population. In 2018, Amazon has a plan to create their second headquarters in Long Island City. They plan to create 25,000 new jobs in 10 years and up to 40,000 new jobs in 15 years. Even though they withdraw this plan, but it's still a good opportunity for us to evaluate the impact. So with the help of our synthetic population, we can find the home distribution of the employees who working in the new headquarters TAZ. So the left figure is a home distribution of employees in TAZ 362 without Amazon, and the right side showing the home location of people with Amazon. And also we have the analysis. We have analyze the impact on modal trips. From the table, we can see that if there's no Amazon, all the modes increase by 3 or 4% is natural growth. But if Amazon moved in, the trips increased really big. Like for transit, it increased nearly 3 times than current, and taxi and for hire vehicle, it increased more than 4 times. This prediction can act as a good reference for the decision maker. And also we can focusing on one certain mode and estimate the trips, the temporal distribution of the trips. The left figure is about for hire vehicle trips without Amazon, and the right side is for hire vehicle trips with Amazon. We can see that the magnitude of the trips increased a lot, and also the trips in the late midnight also increased. The second scenario, Citi Bike Expansion, is also based on the synthetic population. They have the plan to double their service area and triple the number of bikes in the next 5 years. The figure shows expansion plan. So what we did is in the synthetic population, we keep the utility function of Citi Bike the same, but we expanded the service area to the same with their expansion plan. And here is the prediction. The left figure showing the current service, the trip prediction for current service area. And the right side, it shows the trips prediction with the expansion area. The temporal distribution of daily Citi Bike trips are also provided here. The third scenario is based on MATSim model. It's congestion pricing. The charging area is Manhattan and the 60th Street. We evaluate 2 different charging strategies. First is charge 9.16 per enter or leave during peak hour and 3.06 in other time. This charging strategy comes from RPA's proposal. And the second one, we increase the charging during peak hour to $14. This one comes from the CNBC News. In our simulation, we only charging on private cars. There's no charging for taxi and for hire vehicle. Here are the simulation results. The car has a really large decrease after charging the congestion pricing, and with a higher price, the car dropped more. And for other modes, they also increase. For hire vehicle has the highest increase. And since MATSim is an agent-based simulation, we have another advantage. Like MATSim can answer which mode the driver switch to. So in this pie chart, for car drivers, about 58% people keep driving after charging congestion pricing. 20 shift to transit, 9.8, around 10% shift to for hire vehicle, and then about 7% shift to taxi. That's extracted from our MATSim output. We can also calculate the hourly average speed, the spatial distribution across a day. The left figure showing the distribution of baseline model, and the right side showing the distribution under the strategy 2. We also study the impacts of the consumer surplus and revenues. The first table showing the change in consumer surplus. We can see all the travelers are affected by the congestion pricing. People from Manhattan or non-Manhattan have a consumer surplus decreased by around $2 to $3. This means all the revenue collected from the congestion pricing should be applied to address this issue. And about the revenues, our simulation results are pretty close to the RPA's proposal. Under the same strategy, strategy A, our prediction is about 1.1 billion per year, and RPA proposal, they have 1.09 billion. That's really close. And another scenario is a BQX analysis. It's also based on MATSim. The BQX is a new streetcar services. This is a planned route of BQX. After in our simulation, the service time of BQX is 5 a.m. to 11 p.m., 5 minutes headway in peak hour and 10 minutes headway in other time. The travel speed is 8 miles per hour. The figure on the left side is ridership across all the station. The figure shows that in our simulation, the predicted trips are much higher than their proposal, which means like BQX can actually attract more people than their expectation. And the pie chart on the right side, also the advantage of MATSim, we can answer where this BQX rider comes from. 76% people transferred from transit lines, 15% transferred from car. And this is a route load profile in AM for northbound. The x-axis is the distance to the first station in mile, and the blue line shows represents for each station. The last scenario we conducted is COVID-19 impact. The data source we used, the first is Apple Mobility Trends Reports. They have the mode change for driving, walking, and transit. Another one is MTA transit data. First, we generate a new work from home synthetic population based on the work industry, the NAICS code. So this table showing the proportion of work from home in each industry. It's a work from Dinger and Neyman from University of Chicago. We apply this proportion into our synthetic population and generate a new synthetic population for people who need to go out to work during the pandemic. All the secondary, school, and university trips are canceled. And the next step, we recalibrate the mode choice model to feed the ridership data, the Apple report, and also MTA transit data in COVID-19. We perturbate the constant value in the utility function and trying to capture the impact on people's travel behavior. The car, transit, and these three modes will calibrate independently. The table shows the change of the constant value. Only the car has an increase. The transit and walk are both negative, which means like during the COVID-19 pandemic, people prefer car to transit and walk. This change reflects the behavior impacts of COVID on people's preferences for car versus transit works. This is the simulation results of mode shift. Except for back, all the modes decreased from the baseline model. The transit has the most decrease to 74% decrease. And these two pie charts showing the mode share in baseline before the pandemic and the mode share under the COVID-19 pandemic. The next steps of the COVID-19 research, we trying to simulate the recovery from COVID-19. We can use stages from China as a benchmark, and people's travel behavior remain the same. We will trying to simulate the worst case. The stage one, we will reopen the manufacture and construction industry, and which is same to the governor's plan. Keep the school, university closed. All secondary activities remain closed. And in stage two, we will reopen other industry by 75%, open school and university, and recover all the secondary activities. All the results we are preparing a white paper. All the results will be incorporated in that paper and will be available soon. So based on the MATSim scenario analysis, we also investigate some other additional features to improve our MATSim model. First is a link model improvement. In MATSim, trying to save the calculation time, the MATSim adopted the Q model to simulate the traffic, which saved a lot of calculation time, but it is too simple to capture some like realistic features like traffic signal, pedestrian on-street bike parking. So we adopted the bike world traveling holes to improve this Q model. These two figures are the flow density diagram and speed density diagram. We can see with the whole improvement, the figure looks more realistic. And we will use the BPM model to calibrate the BPR function in our improvement model. After this calibration, here are some initial performance. We run the simulation with updated, improved link model in MATSim, and in terms of computation time, our model had similar to the base model. There's no big increase in the calculation time, but in terms of the relative error, our model outperformed the default model. For the 0.1% population, our relative error decreased from 52% to 26%. And for the 1% sample population, our error decreased from 47% to 29%. The second investigation is a multimodal router. We investigated R5, OpenTree Planner, and SBB extension. The R5 and the OpenTree Planner are like independent multimodal router outside MATSim. Both of them can generate multimodal routes given OD metrics. But the problem here is like you need to incorporate all these generated multimodal routes into MATSim. It needs like extra coding work. And SBB extension is a built-in extension in MATSim. There's no need for like a code transfer. But the problem here is like the SBB extension, they can only generate multimodal access egress routes for transit trips. It's not real like multimodal trips. Another investigation is the autonomous vehicle in MATSim. We run a small scenarios for autonomous vehicle with 100 fleet size and 0.1 sample population, about 8,000 agents. The figure on the bottom shows the visualization. The background is a little dark, so maybe hard to see. The green points are the requests, and the right point is serving vehicles. If there's a flash, this means a passenger was picked up by the vehicle. Here are some simulation results. The first showing the distribution of number of requests served per taxi, and the second one showing the number of requests per wait time. There are some shortcomings of our current NYC MATSim model. First is the computation time is high for large scenario. For now, we are running a 4% sample for the city in MATSim. It takes about 11 hours to reach the equilibrium. If you want to have a like larger size, say 10%, it may take more than 20 hours to finish the simulation. This time is really long. And the second one is a Q model in MATSim is very simplistic. And the third one is, even though MATSim is a extendable modular approach, you can write your own module to achieve your purpose. But sometimes it's hard to add features which is not included in the base platform. It needs really high coding skills. So in terms of the shortcomings, the next step for our MATSim research, here are next steps. The first, base model improvement. We're trying to implement and calibrate a new link model in MATSim to improve the performance of the mobility simulation. Another one is we can incorporate the MATSim virtual testbed with other projects. Professor Chow has another research about the microtransit study. We can use our like simulation testbed as a validation platform to conduct that study. And now we are preparing our user guide to give some guidance how to use our baseline model and also give some instructions to how to prepare custom scenarios. And our City Smart Center is also preparing a data observatory. Both the output of our base model and synthetic population will be available online in the future. Okay, thanks. This is all for my presentation. Feel free to ask any questions.
Okay, thank you very much. And we actually already have a few questions from participants. Mm-hmm. So the first question is, I understand that you're continuing to calibrate the model, but currently, how do you account for missing population in your models? For example, those who don't own smartphones?
Actually, the smartphone, we treated in the mode choice model, we treat the ownership of smartphone as availability to for hire vehicle. Like if you don't have a smartphone, it's hard for you to call Uber. So in that way, we treat the simulation. When we do the simulation of the mode choice in our synthetic population, first we decided whether or not this person have a smartphone. If yes, we will apply them like with, we will turn on the availability for them to choose for hire vehicle. If not, we will turn off this option. That's how we, and also for the Citi Bike, we treated the ownership of a smartphone as a alternative, as additional attributes. This may affect people's choice whether or not to use Citi Bike.
What database was used to make the 2016 projections for bike and Citi Bike usage?
For bike, it comes from the 2010-2011 regional household travel survey, but we expanded it based on the population growth rate. And for the Citi Bike, we use the 2016 Citi Bike zonal trip count. So in our synthetic population, we use the least squares estimation to perturbate the parameters to make sure the predict Citi Bike trips are as close as possible to the real traffic count, the real Citi Bike count.
Okay. Which versions of the BPM are you referring to when you make comparisons with MATSim?
I think it's 2010 version.
Okay, another question. In what language do you code additional features?
Additional features of what? You mean?
Like the add-ins, the extensions.
If you want to create from combine the, for MATSim, all the extensions are writing in Java. So MATSim is also Java-based. But for others, you can decide you can generate the data by whatever you want, and put that data into MATSim.
For example, the extension that Ding looked into with the link queuing, was that coded up in Java as well?
Yeah, I think so.
Yeah. Okay.
She may calibrate outside MATSim using other code, Python or something, but
right.
When we implement it into MATSim, all things will be will need to be Java.
Yeah, and I think some of the other features like the autonomous vehicle fleets, that was all that's already an existing extension. So MATSim already has this extensive library of extensions that also include things like features like parking, looking at emissions quantification, looking at freight deliveries, things like that.
Okay, great. So the next question is, could you elaborate on your model on post-COVID-19 simulation? What assumptions were made, or what data are you calibrating to?
The data so first, the assumptions the synthetic population, the proportion of people working from home. That one comes from the University of Chicago. They have a research per how many, the proportion per industry, people working from home. So based on that proportion, we generate a work from home synthetic population. And another assumption is all the school university trip and secondary activity trips will be canceled. Only
just to elaborate on that, when you say you're resimulating population, you're actually keeping the same population, but just setting the agendas to be no travel outside the home, right? For
yeah, that's right. And also the number of population
Okay.
per industry.
And how did you simulate traffic signal control systems? How do you currently do this? Is it possible to simulate different TSC systems using MATSim?
Yeah, I think MATSim has its own signal simulation, but we don't go that way. For our simulation, we calibrate the link capacity to incorporate these features like signals, pedestrians, and on-street parking. We apply a factor to incorporate this loss of capacity on the link. But MATSim has its own like signal simulation extension. If you want to apply different signal system, you can go into that extension to apply your own signal control system.
But the drawback of that is that that could take much more computation, especially at the scale that we're simulating at, right?
Yeah.
So in this case, we're really focusing more on mesoscopic simulation.
Joe, can I comment?
Yeah, of course.
Can you hear me? So we have actually part of this test bed, we have a lower level SUMO simulation that can talk to MATSim if you want to do this kind of a low level control, traffic control type of simulation. So basically you can use MATSim for network-wide predictions and then bring that into SUMO, and then we have a few smaller networks in New York City to try different traffic control and connected vehicle and that kind of strategies. But as a whole, as Joe said, doing this at the network-wide level for the whole city in MATSim is not computationally feasible.
Okay, I have another question here. Does your system use parallel computing to speed up simulation time?
Not yet, but MATSim accepts that features, but we are not expert in that way, so we didn't use that.
We did look into that as well, though.
Yeah, we tried with like the NYU cluster calculation center, but we don't go that way.
Yeah, I think we were finding that those computers were not as, within each one, it wasn't as performing as well as like the way that we were doing it with the computer that we had.
Okay, and I have a question here from someone who'd like you to repeat the data set used for population data for creating the synthetic population.
Mm-hmm. So let me go back for the synthetic population. Here. So do you have any specific question about data sites?
Just if you could just review the.
Okay, yeah, sure. Yeah. So for the synthetic population, first, the personal attribute and household attribute comes from these three data sites: American Community Survey, LEHD, and the SCD forecast data. And the attribute, the table lists which attributes will be used from that data source. And for others, like agenda assignment and also mode choice mode estimation, here are data sources we used. The first one is the 2010-2011 Regional Household Travel Survey. That one we use to generate the agenda and estimate the 2010-2011 level of mode choice model. And 2017 Citywide Mobility Survey, that one we use to validate our city level mode share. The 2016 Citi Bike trip record and 2016 for high vehicle trip count, we use that one to incorporate these two new emerging modes into our existing mode. And the American Community Survey, we use that one to estimate our smartphone ownership data, a model.
Okay, and then if you're using the BPM 2010, mm-hmm. So you're comparing 2016 data to your model. Is this a apples to oranges comparison?
Actually, here we didn't compare our simulated volume to the BPM volume. We just compare the accuracy of the prediction. Like
just to elaborate, the BPM accuracy that was reported in their documentation for when they conducted their calibration. So we were just comparing to see how accurate they were in comparing to their base year versus ours comparing to 2016.
Okay, that's great. So
just one other thing I noticed in the chat screen, people were asking about where to get more information about this. So I think this is going to be on the YouTube channel, and I guess John can share this link with everyone. On the website, and we'll be providing more details on like the white papers, and we're in the process of getting some of this material published as well. So that'll also be shared with people.
Okay, great. Thank you so much for presenting your work today. And thank you to our participants for all the questions that you asked. As Professor Chow said, this presentation will be recorded and posted to the C2 Smart YouTube channel. Thanks, everyone.
Thanks, everyone.
Thank you, everyone. Take care.